hot air balloon. Hot air balloons are awesome. You get this basket and you have this burner and it heats the air and the air fills up the balloon and then the balloon lifts off and floats away. What a crazy idea. Why does it do that? What happens to the gas when we heat it? What happens to the particles? Kinetic molecular theory tells us. What happens to barefoot people on the beach when the sand gets hotter? They move faster. When gas particles' temperature increases, they move faster. This balloon is open to the atmosphere at the bottom. The pressure inside the balloon is equal to the pressure outside the balloon. But these particles are moving faster. So what happens to them? Well, some of them are going to come out so that the pressure stays the same. And then what's left is we have the volume of this gas expanding, right? And some of it leaving. The mass of the gas stays the same, but it gets bigger. Think of a balloon. Well, that is a balloon. Maybe a different kind of balloon. Where is it? This balloon. If you take a balloon and you put it in ice water, it's going to shrivel up and get smaller, right? Because the particles move more slowly. So they're not going to exert as much pressure and the volume's going to go down. Then if you take that balloon and you stick it in some boiling water, the particles are going to move faster and they're going to increase in volume. When we heat air, we increase the volume. The mass of the gas isn't changing, but the volume is changing, so the density changes. Hot air has lower density than cold air, and so hot air will float on cold air just like oil floats on water. So that's why a hot air balloon rises. The volume of a gas increases with its temperature. So here we're graphing the volume versus temperature. And starting here at 0 degrees Celsius, as we increase the temperature of this sample of gas, the volume goes up. This is under conditions of constant pressure and constant amount of gas. So this makes a nice straight line. If we extrapolate the data, which means draw the line past where we have data, we find that it will intersect 0 on the y-axis at a temperature of minus 273 degrees. That number should be a little familiar as the conversion factor between Celsius and Kelvin. Could we get lower than 0 volume? Can you have negative volume? No, that's not possible, is it? So 0 volume is the smallest possible volume. So what this projects is that if we cooled a gas down, when we got to minus 273 degrees Celsius, it would have 0 volume. That is the theoretical lowest temperature. We call it absolute 0. And that's where that number, didn't mean to do that. That's where 273 comes from for the relationship between Kelvin and Celsius. So J.A.C. Charles, this was after Boyle's time. This is last half of the 1700s and early 1800s. He studied the relationship between volume of a gas and the temperature of the gas. And he found that it was directly proportional to its Kelvin temperature. Not the Celsius temperature, the Kelvin temperature. So very, very important. We have to use kelvins with gases. Temperatures must be expressed in kelvins. It's in all caps, it's highlighted, and it's circled in red. Okay, really, really important. Let's add some stars too. Okay, I am not even kidding. That's really important. And everybody forgets now and then, so I'm going to try to just bang it into your brain. Why? Why does it have to be that way? Well, the thing is, the equation of a line is y equals mx plus b, where b is the y-intercept. If we use Celsius, the y-intercept is not 0. And so we can't say that the volume is proportional to the temperature. It would be the volume equals a constant times the temperature plus some constant. That's not going to work. The Kelvin scale gets rid of that constant. So we have to use the Kelvin scale. Kinetic molecular theory explains this as well. If the temperature of the gas sample is increased, the particles move faster. In order for the pressure to be the same, the volume of the gas must get larger. So we talked about that one already. So we can use Charles' law to calculate the volume of a gas following a temperature change or the temperature following a volume change. And this is the equation we're going to use. V1 over T1 equals V2 over T2. Again, all temperatures must be expressed in kelvins. A sample of a gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? We read through the problem, and now we're going to make a table and organize this information. So there's 1 and 2. Volume of 2.80 liters. 2.80 liters. That's our volume column. At an unknown temperature. Okay, that's not a number. When the sample is submerged, okay, this is the new situation. We had the unknown temperature in 2.8 liters. Now we're putting it in ice water at 0 degrees Celsius. That's not the volume. That's over here. We're going to make a new column for temperature. Can we use Celsius in our calculation? No. Let's convert it to Kelvin right here in the table so we don't forget. So plus 273, that means the temperature is 273 Kelvin. When it's submerged in ice water at 0, its volume decreases to 2.57. So 2.57 liters. What is the initial temperature? So we are looking for T1. And it wants it in Kelvin and in Celsius. So we have two columns here, two variables. We have volume and temperature. So we want the equation that uses volume and temperature. We can't use Boyle's law because that has pressure in it. So we're going to have this one, V1 over T1 equals V2 over T2. And we're solving for T1. There's like an infinite number of problems that we can ask for these gas law calculations. And so you need to be able to solve this equation for any variable. This equation has fractions in it, doesn't it? There's a fraction equal to a fraction. My friend, the 7th grade math teacher, tells her students that fractions are the F word because that's how a lot of students feel about fractions. Fractions can get confusing. And so I recommend that we get rid of the fractions first and then rearrange the equation, because otherwise people end up doing crazy things. So how do we get rid of fractions? We're going to do something called cross-multiplying. So cross-multiplying means you take the top of one side of the equation and you multiply by the bottom of the other side. And then the bottom of the first side times the top of the second side. So it's multiplying in an X shape. So when we do that, we end up with V1 times T2 being equal to T1 times V2. And I'm going to keep T1 highlighted in yellow to help me remember that's what I'm trying to solve for. You really have to be able to rearrange equations like this. This is something that's hard for a lot of students, maybe because you just did it so long ago that you just don't remember, or it never really made sense in the first place. I can help you with this, okay? So if this rearranging of the equations isn't making sense to you, please ask me. After class or in lab is a great time to ask me. But I can also help you via text message, or I can even create little videos for you and put them on YouTube. Now we got rid of the fractions, so this is good. Now this is like rearranging Boyle's law, so we're going to divide by V2 on both sides to get rid of that. The V2's cancel out. And now we have our equation that we need, finally. T1 is V1 T2 over V2. Always look at it and make sure you copied it down correctly. Then we're going to put the numbers in. V1 is 2.80 liters, and T2 is 273 Kelvin. And that's divided by V2, which is 2.57 liters. Then I look at my units. I've got liters and liters, those cancel out. I'm left with Kelvin, which is a unit of temperature, so that's a good thing. So I do the math, and I've got 2.8 times 273 divided by 2.57. And that should have 3 sig figs. This whole zero thing, that's kind of sketchy with the sig figs. We're going to assume they meant like right at 0. So I'm going to go with 297 Kelvin. But the question also asks for the temperature in Celsius. We're going to do a lot of Kelvin-Celsius conversions because I've never actually seen a thermometer that was in Kelvin. We don't use Kelvin thermometers. We only use Kelvin in gas calculations. So you read the temperature in Celsius, then you convert it, you do the calculation, then sometimes you have to convert back. So to convert this to Celsius, we're just going to subtract 273, and we're going to get 24 degrees Celsius. So that's all squished down in the corner. So our answer is 297 K, which is equal to 24 degrees Celsius. What would have happened if we had used Celsius in here? What if we use Celsius? 0 degrees Celsius. What would our original temperature end up being? 0. That wouldn't work, would it? Why would the volume change if the temperature was the same? It just doesn't work when you use Celsius. So you got to use Kelvin.